So to describe about data structures in simple terms, it tells us about storing, accessing, and retrieving data in an efficient manner. So it depends upon the different types of data we use to store. Okay. One such data structure is trees. So what are trees? Trees means trees are the data structure consisting of nodes and edges. It's a hierarchical data structure. That's about trees. Okay, let's step into it. What is red black trees first? To describe about red black trees, a red black tree is a balanced binary search tree. So two terms are involved here, balanced and binary search tree, right? Okay, first, what is a binary search tree? To give a detail about it, a binary search tree is a data structure consisting of nodes and edges in which the left child of the parent the left subtree of the parent will be lesser than the value of the parent, and the right subtree will be greater than the value of the parent. So here we can see an example of binary search tree in which we'll be having the root node. The root node is something which is parent to all the nodes available in the data structure. Okay, so here 8 is the root node, and we can see that the immediate left child of the 8 is 3, and immediate right child of the 8 is root node is 10. Okay, so we come down the path. We have 1, 6, 4, 7 in the left subtree, and on right subtree we have 14 and 13. Okay, so as we have said before, a binary search tree is a tree in which a left subtree will be lesser than the value of the root node. So we'll start from 8. So you can see the value of 3, 1, 6, 4, and 7 are lesser than the value of 8. On the right subtree, we can see 10, 11, sorry, 10, 14, and 13 are lesser than the value of 8. If we move further down deeper, we can see the 3. 3 is the parent of 1, 6, and it's the grandparent of 4, 7. We can say it is a grandparent. And yes, we can see that 1 is lesser than 3 as it is a left subtree. And in the right subtree, we can have 6, 4, 7 greater than 3 but less than 8, because we can see that the here 8 is the root node of all these left subtree. So 6, 7, 4, even though it is greater than the value of 3, it lies in the left subtree to the root node 8, right? So the value of all the element nodes in the left subtree is lesser than the value of the root node. And to talk about right node, it applies the same. So a binary search tree is a tree in which the left subtree will be lesser than the value of its parent, and the right subtree will be greater than the value of its parent. That's it. Okay. Let's further move on to another term. We used another term while describing about red black tree, right? That is balanced. So what is balanced? Here we can see, is the tree balanced? No, we can say it is not balanced. Okay, because when do we say a tree is balanced? When do we say a tree is balanced? A tree is balanced if and only if has the height of the left uh, subtree is the height of the left subtree subtracted by sorry, the difference between the height of the left subtree and right subtree is only -1, 0, or 1. What do you mean by these terms? Let me explain you in detail. So avial tree. What is the term about description about avial tree? As we discussed before, right? Balanced binary search tree. So avial tree is one such. It's a balanced binary search tree. So here we can see how a tree is said to be balanced. So consider the first example here. 12 is the root node. And we can see its immediate children are left children is 8 and right children is 18. And further down we move to 8 node 8. We have its children as 5 and 11. And further down we move to 5. We can see its children as 4. So the height, what do you think will be the height of the node 4? It will be 0, right? So the height of the node 4 is 0. If we move up to its parent, that is 5, the height of the node, consider the how to measure the value. As I said before, it's the height of the uh, left tree minus the height of the right? So to 4, we don't have any left subtree or right subtree, right? So it will be 0. That's so the height of the node 4 is 0. And to talk about 5, we can have to 5 we have the left subtree, but we don't have right subtree. So we have one node in the leftmost side of the node 5. So the value will be the value of leftmost child is 1, and we don't have any value in the right side. So 1 minus 0 will be 1. So the value of 5 will be 1. To move up to the node 8, we have 5 and 4 as its as the height of its left subtree, and to the right we have 11. So consider there are two nodes in the left side. So 5, 4. So the value of the left subtree will be 2. The height of the left subtree will be 2, and the height of the right subtree is 11. As it's only one node, 11. So the height will be 1. So 2 minus 1 will be 1. So the value of the node 8 will be 1. What if we move to the root node, that is 12? You can see that in the left subtree, we have to consider the longest path to the leaf node. So here the longest path to the leaf node will be 8, 5 and 4. To the right side, the longest path, there is only one path, that is 18 and 17. So consider there is in the left subtree, the height is 3, and in the right subtree, the height is 2. So 3 minus 2 will be 1. So the value of the node 12, sorry, the value of node 12 will be 1, right? Okay. So what we have discussed before is, if the value is either 0, or it's minus 1 or 1, it's said to be an AVL tree, that is a balanced binary search tree, right? Yes, I have to mention one more thing. An AVL tree is a binary search tree. You can check it if you want. See, uh, the root node 12, the left subtree of the left subtree of the root node 12 is always lesser than the root node, and the right subtree will be always greater than the root node. You can see it. Yeah. And when do we say it is a tree is not balanced? It is not an AVL tree, right? So we have another example here. So consider here similarly. Uh, let's start from the leftmost child, that is 2 on the second example. So 2 has no left child or right child, so the value will be 0. If we consider its parent, immediate parent 4, we have one right, a left child, and there is no right child. So the height of the left subtree will be 1, and the height of the right subtree will be 0. So the value will be 1 minus 0 is 1. And if we consider its immediate parent, that is 5, we have two left subtree elements, and one right subtree element. So 2 minus 1 will be 1. So yes, if we move further up to the node 8, we have, you can see that the longest path from the respective node to its leaf node is 5, 4 and 2. So the leftmost height will be 2, and the rightmost height is, there is one, sorry, 3. 5, 4 and 2, there is 3, and the rightmost side you have only 11, so it is 1. 3 minus 1, is it satisfying? No, it's not, because you have the value 2, which is if the value is not equal to 1, 0 or minus 1, then it's not a balanced subtree, right? So right from this node, node 8, we can say it is not a balanced binary search tree. So it's not an AVL tree. Okay. Actually, our today's topic is about red flag trees, as I mentioned before, right? Why do we? I have to. I introduced about binary search tree and balanced search tree. That is AVL tree, because it's a red flag tree is a tree which holds both the properties of an AVL tree as well as a binary search tree. Okay, so this is how a red flag tree looks like. So as the names itself suggests, it consists of nodes colored with red and black colors. Okay, so yes, and one more thing to add about AVL tree is, what do we need to do if a tree is said to be unbalanced? We have to get it to balance, right? For that, we use the concept called rotation. Here, the left side of left subtree of the node 12 is very much greater than the right most subtree, right? So here we can see the longest path goes like 4, and the right side goes like 2. So 4 minus 2 will be 2. It's not equal to minus 1. It's not equal to 0. It's not equal to 1. So we can't say it is an avian tree, because yes, right? So to solve the solution, we use the concept called rotation. If we rotate the respective subtree that is greater, we can obtain a balanced binary search tree. That's what the concept is all about. And we'll see the concept later in the forthcoming videos. So yes, this is one more thing to add on avial trees. Talk about red black trees. You can see, yes, as I said before, it's consisting of the nodes filled with colors red and black colors. Okay, and why do we prefer a red black tree over a avial tree? As I said, An AVL tree is a balanced binary search tree. To talk about red black tree, it's also a balanced binary search tree. Then what is the purpose of using red black tree over AVL tree, right? So an AVL tree, to get an unbalanced tree to a balanced one, we have to do a lot of rotations, depends upon the data structure. But in case of red black trees, more we can't do more than we only doing two set of rotations is more than enough to get a red black unbalanced tree to a balanced one, right? So how do we do that? Let's see it in detail. First, there are some properties regarding the red black tree. So the root node of the red black tree should always be a black node. Okay, this is one condition. And the next condition is you can have two or three more successive children on black nodes, but you can't have two consecutive red nodes. Okay, you can see here we don't have any two hierarchical consecutive red nodes. If the 12 is black, we can have 5 as black, and we can have 3 as black, even we can have 12 as black. But if a node is red, you can say it's 12 is red, it means you can't have either 7 or 11 as a red node. It should be black node. This is another more property. And the third property is always if you insert a new node into a red black tree, that means you are inserting a new node element into it, it should be a red node. And the fourth property is uh, the leaf node, that is the last node of every hierarchical order, should be a black node. Okay. Okay. So if I said if you insert a new node, you have to insert it as a leaf node, right? And I said the next property will be the leaf node should contain only a black node. So what do we do if we insert a red node into as a leaf? So we have to rotate it accordingly in order to get in such a way that the black node holds the value of a leaf node structure. And here, in the first example, we can see the root node is 12. No more than one node is its immediate hierarchy, is its consecutive hierarchical order of another node in case of red color nodes, right? And to talk about black nodes, we can have as much we can. And yes, and one more property we described is we can't have a red node as a leaf node, right? But you can see that the node 4, 6, 8, and 14 are the leaf nodes, but they are in red color. Why? Actually, this is not the leaf node, the real leaf. You can see in the second example, which consisting of nil, nil, nil in every of its. Every leaf node contains a further data in which a left child and right child will hold the value of nil, which means there is nothing, no more value, but a data structure is created. If you want to insert any node, we can we can replace the value of nil with the node value, right? That's the concept. So it's hidden actually. So this is what the second example is what a real structure looks like. So every child will have a black node with the value of nil. If you want to insert a new value, then we will insert in the value. That's it. So yes, this satisfies all the properties, right? We have to check one more thing we have to check is it's also a balance, a binary search tree. So consider here the root node is 12 and the leftmost subtree will have the values less than or equal to 12. So here the one red node is having the value of 12, which is equal to, it's not more than 12. So we can have it as a left side. And one more thing to add is the right side is always having the value greater than it's satisfying the binary search property. To talk about levels, here the levels are based on the properties as I have mentioned before. If one of the properties missing or it's not satisfying any of the properties I have mentioned before, the 6 properties, means that it's not a red black tree. We have to convert it into a red black tree. We have insertions, deletions, operations in red black tree, which we will see in forthcoming videos. Thank you for today's video.